Okay, folks, let's get it started. Good afternoon. We have our homework number 5, I believe, due today. I am not going to go through the solution right now, and I'm not actually going to post the solution until tomorrow morning. There's one distance student who had a problem, so he asked me to give him a little bit of an extension. I have already graded your homework number, I believe, 3 and quiz number 3. The grades are on Blackboard. I forgot to bring them over here today to the class so that you can take it. There is one student whose homework assignment is missing. This is the homework assignment that some of you submitted, and then I extended it, and you guys came back and picked up the homework assignment. So if you have by mistake taken someone else's homework assignment, go ahead and check your sheets and notes and stuff, and let me know if there is extra homework assignment that doesn't belong to you in your stack of papers. Any questions? Yes.
I guess I cannot ask from the homework, right?
Yeah, just wait until next session, like on Thursday. Okay. Other questions? Okay. So the topic that we started covering last time was multi-level power electronic converters. So a classic single pole double throw switch can give us only 2 levels, basically. Let me see if I can. So a classic single pole double throw switch gives us 2 levels of voltage. Your pole voltage is either, if the top switch is involved, your pole is connected to the voltage of throw number 1, or if the bottom switch is involved or engaged, then your throw is connected to the second throw, basically. So your pole is connected to the second throw. So you only have 2 levels. Sometimes these 2 levels is enough, sometimes it is not, depends on the application. Sometimes you would like to have a high quality in terms of total harmonic distortion output voltage. And that, the indication is you need to have more number of levels. And sometimes the limitation is on the switch. You are trying to achieve a high voltage kind of an application, like your voltage is, your peak value of the peak value of the AC signal that you're trying to synthesize, let's say, is 2000 volts. But the IGBTs that you have are only 600 volts or 1200 volts. So that means that one particular switch cannot handle your voltage. So you kind of have to come up with a configuration that the stress on individual switches is low, but at the same time you can synthesize a higher voltage. So that's the idea behind multi-level power electronic converters. They are becoming very popular. Like 10 years ago, if you were in a conference in power electronics, there was like a little session on, or half a session on multi-level converters. Now there's many papers submitted in this particular area. There's a good research going on. The first one that we covered was Cascaded H bridge converter. As the title suggests, you have one H bridge, gives you 3 levels: 0, positive VDC, and negative VDC, depending on the switch configuration. And then you basically cascade these guys with each other to achieve higher voltages, like something like this. We cascaded 2 of them, and we were achieving basically 9 levels, up to 9 levels. Now, the diagrams that I have here, I am showing kind of a staircase switching scheme. But remember, this does not necessarily have to be a staircase, in a sense that it could be PWM. Like, you can actually switch between these 2 levels as much as you want, and also here. But since drawing those guys is a little difficult, I'm just using the staircase. Also, for the cascaded one, you can still do PWM, meaning that you don't have to stay here. You can, for instance, go up and down here, and then up and down here, or something like that. So remember, my drawings are all based on the staircase assumptions, but then you can do PWM or state space, vector kind of a space vector modulation. The second topology that we started the discussion is diode clamped multi-level converter. Let me So the first one is so the idea behind diode clamp multi-level converters is how we can implement a single pole, triple throw switch. So I have a diagram over here. You can actually see what we are talking about. So in a classic single pole double throw switch, there are only two states. Either the top throw is engaged or the bottom throw is engaged. Over here we have three throws, so we have three states basically. So how are we going to do that? And then once or if we manage to build such a switching scheme or switching topology, then we can achieve three levels. Depending on the position of the throw, we can either have, if the top throw is engaged, then our pole voltage is VDC1 plus VDC2. If the middle throw is engaged, then it is only VDC1, and if the bottom one is engaged, it is shorted or zero. So in order to implement this, we know how to realize a single pole double throw switch. So using those building blocks, I'm using actually three of them, one here, two here, and the third one is over here. I can manage to build a single pole triple throw switch. There is a little bit of a redundancy here. The redundancy comes in that when we want to have the middle throw engaged, we have two options. One is turn this switch on and also turn this switch on. So then the middle throw is connected, so there is a path for the conduction of the electric current. Or the second option is turn this switch engaged and then turn this other bottom one engaged. So again, you're achieving the same goal. The middle throw is engaged. Because of this redundancy, when it comes to switch realization, we can actually reduce the number of transistors required. In terms of switch realization, we have already seen switch realization for a single pole double throw switch. Here voltages are assumed to be positive. Most of the times, 99% of the time, they are positive, but the current is bidirectional, so the application that we have in mind is more like an inverter basically. So we have the classic switch realization for a single pole double throw switch with a right half plane, bidirectional current, unidirectional voltage, and then we kind of using three of them. And then because of the redundancy that I just talked about, we realize that we don't really need this switch over here, and we don't really need this bottom switch over here either, because, for instance, if you want to have the middle throw engaged, you basically have a switch over here, so you turn this switch on, and then the conduction of the current is going to be like this. So we don't really need those two switches. So instead of having 3 times 2, which is 6 transistors, we only need 4 transistors. So we are kind of saving in terms of the number of transistors. In terms of diodes, we cannot eliminate any of these diodes, so we still need 3 times 2, 6 diodes. All right, so any questions so far? All right. Now, what happens is if you open up a textbook or a paper, they don't really draw this particular diode clamp topology this way. Let me draw it the way that you may actually face once you are looking at a particular paper. It is usually drawn this way. So I'm not doing anything fancy, I'm just redrawing the circuit over here. So all of these transistors have, or I mean in this case I'm drawing them using IGBTs, they have the anti-parallel diode because the current is bidirectional. This is the pole, and then I have two diodes. Maybe a little bit higher. Oops. A little bit higher. Okay, so something like this. And I just labeled this to be VDC2 and then VDC1. Okay, so most of the time it's assumed that this is the ground. I'm not going to draw it right now, but later on we're going to talk about it. All right, so a lot of times when somebody's talking about a diode clamped cell or building block, they're talking about this. The reason that it is called diode clamp is because of these diodes. Basically what these diodes do in a particular operating condition, they are clamping this point to this point. So that's why it's called a diode clamp topology. Please note that just because these two switches are drawn in this configuration, they are not complementing each other. There could be a situation that both of these transistors are on, and that situation is when you want to have a conduction of current in this path. All right? So those transistors, let's call them transistor 1 and 2, are not complementing each other, and therefore they are not forming a single pole double throw switch. Okay? So if somebody asks you, identify the single pole double throw switches in this circuit, one is this one. These two switches are complementing each other. The other one is this one. And the third one is this one. All right. But they are drawn in a way that is a little bit confusing, okay? So please remember, we have 4 transistors and 6 diodes. Okay. And by the way, this particular one is called a 3-level diode clamp. And we're going to see a 5-level in a few minutes. 3-level diode clamp. Okay. Any questions so far? Okay. So the next question would be, okay, in this diagram, we have VDC1 and VDC2. First thing that you're going to observe is they are the two sources, assuming that they are two independent sources, are placed in series with each other, which may or may not be a good thing. Remember, there is a distinction between this topology and the cascaded H-bridge topology. In the cascaded H-bridge topology, the sources were kind of floated, okay? They were not placed in series with each other. Over here, this could be considered as an advantage because these two sources are not floated. They are kind of in series with each other. So in a general case, what we do is we don't have two independent sources. Usually we only have one source, okay? So how is it that we can get two independent sources from one source? The trick is very simple. It would be using capacitors. How to generate okay. So what we usually do is we only have one DC source, and then we kind of split the voltage of this DC source using two capacitors. The value in terms of size of these two caps They are the same basically, like they are both of them are 200 micro or something like that. In terms of what size capacitor we should use, you should look at the amount of electric current that is charging and discharging these capacitors, as well as the switching frequency, the charge and discharge, basically the amount of charge and discharge, and make a decision. So basically those determine the ripple in the system, the ripple of these voltages. Okay, I'm assuming that this is my ground now, and I have a load connected to this ground. Okay, let's consider we are using actually this capacitor for like a bidirectional kind of a DC to DC converter kind of a thing. I'm going to label this to be I out. Okay. So please remember C1 is almost the same as C2. And our ideal goal is to have VC1 to be almost the same as VC2. And almost similar to Vin over 2. Okay. So for this to happen, we got to make sure C1 and C2 are large. Again, how large? Kind of like when we were designing the Bach topology, we assumed that the output capacitor was large. And large meaning that the ripple of the AC ripple of the cap is much smaller than the DC component of the voltage of the cap. And one thing to remember, if you're actually using a circuit like this, you got to make sure this current, I just labeled it to be IX. On average, your switching scheme should be in a way that on average IX is 0. Okay, has to be 0. Now, why is that? Because otherwise, if IX, for instance, is positive, it means that on average, this capacitor is getting charged and this capacitor is getting discharged. So after a while, your top capacitor charges all the way to Vin and the bottom capacitor is 0 basically. Okay? So if you have a particular switching scheme in mind or a particular direction for your electric current in mind, you got to make sure that on average IX is 0. Otherwise, the converter is not going to work. We have a table here to kind of explain how different levels are selected and which capacitor is being charged and which capacitor is being discharged. So let's pretend I out is bidirectional. It could be positive sometimes, it's negative sometimes. And we are in position 1, meaning that the top throw is engaged. What happens to the input voltage? So obviously if the output current is positive and the top throw is engaged, the power is coming out of your source and going to the load. So your input voltage source is being discharged. And when the current is negative, it's being charged. Okay, what about C1 and C2? Nothing really happens to C1 and C2, so we don't have to worry about them. Okay. because they are not even engaged, because throw number 2 is not engaged. We only care about C1 and C2 when throw number 2 is engaged. Here, throw number 1 is engaged. And what about the output voltage? Let's call this the output voltage. It's VDC or VN. All right, something like this. So this was when the switch is in position number 1. What about position number 2? Again, there are two possibilities. I out is positive, or it could be negative. If I out is positive, we are having a discharge for the overall source through C1, and then we have a charge for the source if the current is negative. What about C1 and C2? C1 is going to get charged. C2 is going to get discharged. And C2 the opposite, basically. So C1 and C2 are a series with each other, and VC1 plus VC2 at any given time is Vn. So if one of them is getting charged, the other one has to get discharged. Discharge, and this is getting charged. And we are looking at VDC over 2. Vin over 2. Okay. All right. So, the point that this table is trying to highlight is, if you are using this in an application, you got to make sure C1 is not constantly being charged, or C2 is not constantly being discharged, or something like that. So technically, you got to equally select these two modes. Therefore, you can only use this application, this converter for this particular application, when I out is bipolar, and in a symmetric way bipolar. Sometimes it's positive, sometimes it's negative, and in a symmetric way. And finally, our last situation is when the switch is in position number 3. Again, I out could be positive or negative. The source is not engaged, so nothing happens into the source. C1 and C2 are not engaged. Nothing happens to them. And our output voltage is basically 0. So we can create these 3 levels using the 3 positions that are available to us, using only one source. And the levels are 0, half of the source, or the entire source, assuming that our output on average, our Ix on average should be 0. So let me put it over here. On average, Ix has to be 0. Okay. So this is one way of doing this, assuming that the bottom line is your ground, or you can do it a little bit differently. That is assuming that you are connecting this to, let me draw it first. The other option is you have a source which does not have a middle point, and then you're putting these caps in parallel with it. But then you assume that this is your ground. Okay, so the middle point between the two caps is your ground. So then still you have C1, C2, Vn, okay, so something like this. Still, you have to make sure on average the current that charges or discharges the capacitors is 0. I have almost a similar table for this mode of configuration as well. Let me just draw it. C1, C2, and V out. Okay, so position 1, I out could be positive or negative. If it is positive, our source is being discharged, otherwise it is getting charged. C1 will be discharged, and C2 will be charged. And when the current is negative, the opposite happens. We have charge here and discharge here. And the output voltage is VDC over 2 in both cases. Okay. Then switches in position number 2. The current could be positive or negative, the output current. Nothing is really engaged. We are basically shorting our load, so our output voltage is 0 basically. So nothing really exciting happens here. And then you select position number 3, and then depending on the polarity or the direction of your current, you have your source being charged or discharged. Then C1 is being discharged and C2 is getting charged. And when the current is negative, the opposite happens, charge and discharge. And your output voltage is negative VDC over 2, or negative Vin over 2. Let's say Vin and VDC are the same. So again, when it comes to balancing C1 and C2, you should actively or in a passive way, assuming that there is symmetry in the system, make sure that the amount of discharge that is, the amount of electric charge that is coming out of C1, that is when you're in these two modes, should be equal with the amount of charge that is going into C1. Otherwise, gradually, capacitors are not equally, basically the voltage of the capacitors are not equal with each other. So we kind of have a bipolar output voltage. So we have some output voltage that is positive here, and then some output voltage that is negative. So we have a output voltage is bipolar. Bipolar. In the previous case, the output voltage was unipolar. It was always positive. So probably have to use it, for instance, in a three-phase configuration. Something like that. All right. Any questions so far? All right. So this was about, we had a wild idea of having two sources or pseudo sources like two large capacitors. And then how is it that we can generate three levels using a single pole triple throw switch. Now we can extend it and say, what if we have three pseudo sources? Can we use a single pole quadruple throw switches and then kind of extend the number of levels to higher levels? The answer is yes. The steps are almost the same, so I'm just going to plot the kind of the outcome. So what if we are looking for a single pole kind of quadruple throw switch? All right, something like this. Okay, so we have four possibilities. Throw number 1, number 2, number 3, and number 4. Okay? So either we have to use three independent sources like VDC1, VDC2, VDC3, or have one source and then use three large capacitors to split them. And that's what usually we do in industry. So let me just draw, assuming that we have only one source and three large capacitors. So this is 1, this is 2, and there is the third one. Maybe I should have drawn the capacitors at the end. So we are using six transistors, and all of these transistors have the anti-parallel diode for the case that we are working with, which is the most of the cases anyway, a bidirectional output current. Okay, so this is your I out, or basically the pole current. Then we got to use 4 other diodes, which are the clamping diodes. So one diode is here. Let me draw it a little bit higher. And then there's a diode here. Okay. So these are 2 of our clamping diodes, and then there's 2 other more. Okay. And all right. So now we got to kind of hook up these 3 capacitors to them. So unfortunately, my drawing is not very good. This goes here, and this one goes here. Okay, and that's it. And then you have your main DC source. Okay, so this is going to be our single pole quadruple throw switch, basically. So technically points 1, 2, 3, and 4 here. 1, 2, 3, and 4 are 1, 2, 3, and 4. So technically, depending on which one of these, and I'm going to explain a few of them, which one of these switches are involved, we can argue that the output voltages could be 0, it could be VDC1, it could be VDC1 plus VDC2, or it could be VDC1 plus VDC2 plus VDC3, which is a VN anyway. Okay? And then we can extend this idea to even more number of levels, like 5 levels and beyond. So we have 4 levels here. And we are using 6 switches and 10 diodes. Okay. All right. So let's consider a few cases. For instance, I'm going to use a kind of, I hope you guys are not colorblind, let's use color of red, and our requirement for color of, okay, let me first of all highlight the output voltage. Let's say this is my output voltage. Okay, and okay, so let's start with red. I can find myself in a situation that I out is positive, and we would like V out to be VDC1 plus VDC2, or basically 2/3 of the input voltage. Okay, so the question is which one of these switches we should turn on, basically. So remember, I out is positive. So what we got to do is, we want to select node number 2. Okay, so we are trying to select this node and short this node to our pole on the output side. So what I got to do is, and the current is positive, by the way, so I don't have to worry about this diode. The diode is going to be forced to be on. All I got to do is I got to turn this transistor on and this transistor on. And there you go, you have it. So if I label these switches, let me call them switch 1, 2, 3, and then 4, 5, and 6. Okay, so in order to achieve this goal, all I got to do is turn S2 and S3 on. All right, so it works. Now let's consider another one with blue this time. Let's say our objective is we find ourselves in a situation that I out is, let's say this time is negative, and we would like our output voltage to be tied to, I don't know, VDC1, which is 1/3 of the input voltage. Okay, so remember I out is negative. So before we do that, so let's say this is in this direction. I out is this time negative. So now I have to, okay, the current is coming in. I have to turn S4 on and S5 on. That's it. Okay? So you got to turn S4 and S5 on. And you're in business. Okay. Sometimes these switches are turned on and off together. So again, remember these switches are not complementing each other. If somebody asks you what switches are complementing, in this diagram, what switches are complementing each other, your response should be, okay, the figure is going to get a little bit busy, so let me just copy and paste it. Let me make it a small first. Okay, now I gotta erase the extra stuff. Okay, so if somebody asks you, like a sketch or plot the switches or the diodes, because we consider a diode as a switch as well, that are complementing each other, or they are forming a single pole double throw switch. So your answer should be like this. These guys are complementing each other. Okay. Then these guys are complementing each other. Then, assuming that you don't run out of colors, these two guys are complementing each other. So they are forming a single pole double throw switch. Then these guys are complementing each other. And then finally, this transistor and this diode are complementing each other. Okay, so this is how they look like. All right, any questions?
How do we exactly get to the conclusion that which switches will complement?
Oh, it's not a conclusion. This is how they have been designed, but the way it's being drawn is a little bit confusing. Honestly, I can't tell you how, but just again, going back to the way we kind of constructed our first 3-level switch using single pole double throw switch as well. We were basically put a bunch of these guys over here, and then we realized for the realization of this complementary switches, we only need a diode in the bottom, something like this. So these diodes are complementing a full transistor anti-parallel with the diode. Then in the very center, we always have these two guys that are full switches with two diodes complementing each other. So almost the same trend. So have this in mind, like a bean kind of a thing. It's like we have an extra bean over here and an extra bean over here, something like that. So it spreads out.
What's the advantages of this setup as opposed to like the pulse width modulated and filter because all it's doing is selecting an output voltage, correct?
That is right. The advantage could be Okay, so let's talk about the advantage. So let's say you have IGBTs that are 600 volts. Okay, so you have selected IGBTs. So you are, to realize these switches, you are using switches or IGBTs that are 600 volts and diodes that are 600 volts. So we have, let's say, 600 volts IGBTs and diodes. Okay, so technically from here to here I have a maximum of 600 volts when this switch is off. This means this capacitor can go, I mean, let's say to 400 volts, okay? Ideally 600 volts. I have 400 volts here, 400 volts here, 400 volts here. So I have a 1200 volt source here. That means my output voltage can get as high as 1200 volts using IGBTs that are not 1200 volts. They're actually smaller than that. And then this is one advantage. The other advantage is having an extra level. That's another advantage. So my levels in the output are 400, 800, and 1200. Okay, so that's the second advantage. You may argue that I don't care about the second advantage, and in order to accommodate 1200 volts, what you can do is, obviously what you can do is, you can just put 3 IGBTs in series with each other. And let's say this is your pole, and assuming that your current is bidirectional and everything, okay, so this could be another solution. Technically, you are still using 6 IGBTs, and let's say each IGBT is 600 volts. So the 3 of them in series can easily handle up to 1600 volts. So 1200 volts is nothing. But the challenge that comes in this configuration on the right-hand side, as I said, we don't have the 3 levels. We only have 2 levels, which is either 0 or 1200. So we lost the, I'm sorry, previously we had 4 levels, 0, 400, 800, and 1200. So we have already lost 2 levels. So in terms of THD, we may argue that on the left-hand side we can provide a better THD. The other thing is, if we want to have a conduction of current, for instance, the top throw being engaged, we have to turn these transistors on at the same time, which is quite challenging because our gate drivers may have a slight differences in terms of their time delay. The switch, even though they are coming from the same manufacturer, one of them might be reacting 2 nanoseconds faster than the other. As soon as one of them is on, assume that, for instance, this transistor is on, but the other 2 haven't had a chance to turn on. So the other 2 are basically bearing 1200 volts, which is getting scary. Now imagine then this one turns on. So the bottom 2 are on, the top one is handling 1200 volts, but it was a 600 volt IGBT. So boom, it actually smells and you have to replace it. Timing between these 3 transistors to turn them on and off becomes really crucial. So then you have to use, some clampers and RC circuit around that to do that. So technically you can achieve putting transistors in series with each other. It's not as reliable as a multi-level topology, basically. And in a multi-level, I mean the converter that I have on the left, you only added 4 diodes and 3 capacitors, and then as well as 2 extra levels for your voltage, which is better. Any other questions? Okay. So let's move on. So now, before I introduce the third category of multi-level converters, which is flying capacitor converters, let's try to kind of hybridize or combine what we have learned so far. H-bridge converters and cascaded cascaded H bridge and diode clamp converters. So let's open up a kind of category here. I don't know what to name it. Let's call it 2.5. And that is hybrid. Or hybrid H bridge and diode clamp. Okay, so what do I mean by hybrid? Remember when we were talking about H-bridge converters or cascaded H-bridge converters, we used single pole double throw switches. So now that we have learned how to build, for instance, a single pole triple throw switch, maybe we can use the same idea to increase the number of our basically levels. So let me draw the classic one. So the classic H bridge was something like this. I put a single pole double throw on the right, and I put another one on the left, and I kind of said, okay, this is my V out from here to here. All right? All right. Now we can do almost the same thing using, instead of 2 single pole double throw switches, we can use 2 single pole triple throw switches. So one on the right and one on the left. All right, so I'm going to label this to be VDC1. Okay, and it depends on what you define as your output voltage. Okay, over here I'm doing a little bit of a different thing. I just call this, let me call this, in order to understand it better, I just call this node to be X. This is Y. Obviously my overall output voltage is Vx with respect to Vy, but let me just do a little bit of a grounding here as well, and we are going to see why. So this is my overall output voltage. So remember, in order to implement a single pole triple throw switch, we needed 4 transistors and 6 diodes. Now we are using 2 of them. So we need 8 switches or 8 transistors and 12 diodes. But let's take a look and see what our output voltage basically looks like. So I'm going to create a table here. And I'm going to label these to be, okay, I'm going to call this switch S1, switch S2. S1 could be in the first, second, or third position, and S2 could be in the first, second, or third position. So we have 3 possibilities on the left, 3 possibilities on the right. We have a total of 9 basically possible states. So ideally, we can, assuming there is no redundancy in the system, we can go as high as 9 levels. But there's a little bit of a redundancy. We can go up to 7 levels, basically. So we have 1, 2, 3, then 1, 2, 3, 1, 2, 3. Okay, so this is all possible, switch selections. Let's look at Vx. So when I say I'm going to look separately at Vx, then Vy, then Vout is Vx minus Vy. And Vx and Vy obviously are with respect to the ground. Okay, so if S1 is in position number 1 and S2 is in position number 2, X and Y are both shorted to the top of the top DC source. So here I have VDC1 plus VDC2. Okay, I'm going to run out of space. I'm going to erase this and plot them a little bit further from each other. VDC1 plus VDC2. And V out is going to be 0 anyway, because like we are shorting X and Y to each other. And then in the second case, if S1 is in this first position, VDC1 plus VDC2. And even here we will have VDC1 plus VDC2. Here VDC1 and then 0. So overall my output voltage would be VDC2 and 0. Oops, sorry. VDC1 plus VDC2. Okay, so these are so far 3 possibilities. Then if my switch number 1 is in the second position, I have VDC1 for Vx. And then I have 0 for Vx. Then for Vy, we have to look at S2, and then I have, it's in the first position, so VDC1 plus VDC2. Only VDC1 and then 0. And then VDC1 plus VDC2. Only VDC1. And then finally 0. And the difference between these two columns is my output voltage. So then it becomes negative VDC2. It becomes 0. Then it becomes VDC1. And then negative VDC1. Negative VDC2, and then negative VDC1, and then 0. So total, I was expecting to have 9 possible states. 3 of them are giving me 0, so there is a redundancy there. So I can get up to 7 levels. Now, are these levels close to each other or far apart from each other? It depends on the numerical value that you choose for VDC1 and VDC2. For instance, if you choose VDC1 to be equal to VDC2, and I just label them to be E, then I am going to have actually more redundancy. Then I have 0 here, E, 2 times E, negative E, 0, again E, negative 2 times E, negative E, and then 0. So more redundancy because VDC1 and VDC2 are the same. There's not a significant difference between them. So I will be coming down to 5 levels. Okay. Then you can argue, are VDC1 and VDC2 independent sources or not, or are they capacitive? I'm not going to really go into the details of that. You can actually make it happen in a way that they are actually capacitors. Okay, so if they are actually real capacitors, the converter, including its switch realization, it is going to look like this. Okay. Okay, so this is only one of the legs. And remember, these are all diode clamps, so I still need a diode here, a diode here. Okay, and this is connected to the middle of a capacitor. Okay. So this is one of my legs. And the other leg is basically similar to this. I'm just going to plot it here. Okay. So we are feeding it with the same source. We still need those two clamping diodes. And they're still connected to this middle point. Okay. So my two outputs is, one of them is this pole over here. And the other one is this. So you can argue that this is like a single phase inverter with a maximum of 5 levels, basically, something like that. And yes, these converters have been built. They look a little bit busy, but once you become familiar with them, you are going to realize there is some modularity in them, and they are not as difficult to build as you can argue, especially these days, because semiconductor devices are very cheap, so it's not going to cost you much to build a converter like this. All right, so you can see that this was just an example of how we can hybridize the idea of a cascaded H bridge topology with a diode clamp topology and come up with numerous new topologies. Okay. Any questions so far? Okay, so we're going to get to the third category of multi-level basically converters, which is the third category is called flying capacitors or capacitor clamped multi-level converters. So multi-level flying capacitor or sometimes they are called capacitor clamped. Multi-level. Okay, as the name suggests, we are expecting to see a lot of capacitors in these converters. Let's just start with the very basic block that we are very familiar with, which is a capacitor feeding a, okay, we do not necessarily have, by the way, we do not necessarily have to start with capacitor. Let's say this is, let's assume it's an independent source. It's a solar panel or a power supply, like a floating thing. So the very basic cell that we are very familiar with is this. So depending on the position of the switch, we can generate two levels. Now, let me extend it with a little of a trick to this. It's almost still the same. Basically, now I'm using, instead of my single pole double through switch, I'm using two single pole single through switches. But the operation, remember, the same. Either the top switch is on, the bottom one is off, or vice versa. They are complementing each other. They are not, at any given time, one of them is on, the other one is off, something like this. And then I can kind of repeat this structure over here. And then I have another source. And then keep going. On the left, you can keep adding sources, presumably independent sources, but later on we are going to see that we don't have a lot of independent sources available, so it's better to have a capacitor replacing most of them, except for one. So I'm just going to label this to be VDC1 and VDC2. Okay, this is our output current. Now, where is this output current going to come back? It is going to come back here. Oh, let me just say this is our load or whatever it is. So if we have a return path for our electric current, and I will label this to be S1, and to make sure we don't forget that these are complementing each other, this is S1 prime, and this is S2, and then S2 prime. Okay? So assuming which one of these switches is engaged or not, so let me, if we only have, so I call this VDCN. If n is 2, or we only have two independent sources and four switches, S1, S1 prime, S2, S2 prime, let's take a look at this table and see how many output voltages we can generate. S2, S1. So we have two possibilities for S1, two possibilities for S2, and obviously the other two are complementing these two, so they are not independent, they are dependent. So we have a total of four possibilities. Now looking at V out, for instance, if S1 and S2 are both on, V out is VDC2. If S1 is on and S2 is off, or S2 prime is on, basically V out will be VDC1. Wait a minute. V out will be VDC1. Let me see, S2, S1. Somehow my notes are, okay, let's look at this. S2 is on, so I have short here. Oh, this is on. Okay, so this is VDC2 minus VDC1. Okay, so basically the way it's working is, let me highlighted in red. So, oops, VDC1. So technically our loop is, this is on, this is on. So this is our loop. So if you see, it's like VDC1 is flipped and is added to the top of VDC2. So we have VDC2 minus VDC1 applied to the output, basically. And if S2 is off, S1 is on. At the same time, S2 prime is on, S1 prime is off. We are looking at VDC1. And if they are both off, output is 0, basically. Okay. So with this structure, assuming n is 2, we can generate four basically levels. And in terms of switches, let me write it down here. So we have 4 levels. We have 4 transistors, and I'm going to explain it. And 4 diodes. Okay. So in terms of switch realization, first of all, our switch realization should be bidirectional because I out could be positive or negative, and it's going to be realized this way. So for S1, we will have something like this. Okay? And all of them are the same, basically. You just have to copy and paste it. As long as VDC2, so for S2 we have the same, for S2 prime we have the same, for S1 prime we have the same. As long as VDC2 is greater than VDC1. So let me write it over here. Is correct. If VDC2 is greater than VDC1. Okay? So it's very easy. If you have independence, later on we are going to see all of these are capacitors actually. They are not independent sources. But if you happen to have independent sources, all we got to do is pick the larger one and put it all the way to the left, and then kind of sort them in a way that the one that on the left is the largest one, and then gradually you decrease it to the one on the right, which is the lowest one. If that is the way you are ordering your independent sources, then for all of your switches, you are going to have this very kind of symmetric, classic switch realization. Yes?
Greater than, not greater than, equal to?
Greater, not even if they are equal, it's okay. But practically, you're going to realize that they are far away from each other in terms of values. Any other questions so far? Okay. So if you have independent sources, we are good to go. As it turns out, we don't really like independent sources. And by the way, again, you realize here that our independent sources do not have a common ground, or they are not even in series with each other. So for instance, if you look at this guy over here, it is kind of floating with respect to VDC2. Depending on if S2 is on or S2 prime is on, you can see that source is kind of up in the air kind of a thing. So a lot of times happens that instead of independent sources, we would like to have capacitors, replacing most of them except for the largest one, which is actually our main source of power. So to entertain that idea, let's consider a case that VDC2 is twice as much as VDC1. For instance, VDC1 is 100 volts and VDC2 is 200 volts, something like this. So we will get, instead of VDC2, I'm going to write everything in terms of VDC1, 2 times VDC1. Then instead of VDC2 minus VDC1, we just get VDC1. And again VDC1, and then 0. Okay? So now if you follow this particular ratio between these voltages, we are going to lose one of our levels. So we only have 3 levels here. Okay. But we are going to gain something, which is redundancy. Okay. So we have a redundant state. And then later on, we can argue that in one of these states, like if we replace VDC1 with a capacitor, in one of these states, this capacitor is getting charged. In the second state, it is getting discharged. So we can always place a capacitor there and don't worry about this capacitor going out of totally being charged or totally being. You can actually balance the voltage of this capacitor or regulate the voltage of this capacitor at half of VDC2, something like this. So we have some redundancy. All right, so I'm going to assume that, let's look at the charge and discharge pattern of these basically sources. For now, they are still sources, but later on we are going to realize that VDC2 is actually a source, then VDC1 is a capacitor which is regulated at half of that source. So let's call it source 1, source 2, and source 1, which is VDC1, will be discharged. Oops, the other way around. Let's do them source 2 and source 1, because source 2 is on the left, source 1 is on the right. So this will be discharged, and nothing, and nothing. And when it comes to source 1, nothing in the first mode, then it will be charged, and then discharged, and then nothing. And this is assuming that the I out is positive. Okay. If we assume that the output current is positive, so by the way, output current not necessarily has to be bidirectional. It could always be positive. For instance, we are looking at a DC to DC converter, okay? Or it could be negative or positive, doesn't matter. If we even assume that our output current is always positive, you can argue that there is a possibility to, instead of source number 1, use a capacitor, and depending on what mode we are selecting, we can sometimes charge this capacitor and then sometimes discharge this capacitor. So ideally, we have the opportunity to regulate the voltage of this capacitor at half of the input voltage. So that's why the term flying capacitor comes in, and then we are going to actually further study this next time. And so this was, if you open up a paper about flying capacitor, you won't see them drawn this way. So next time we are going to actually see how exactly they are drawn. So just remember for next time, we have the opportunity, regardless of the polarity of the output current, we have the opportunity to charge and discharge source number 1. So it could be actually a capacitor. It doesn't have to be an independent source. Any questions so far? All right. So I'll see you guys on Thursday. Remember, next week on Tuesday, we have a quiz which will be covering multi-level converters, okay?